The powers of a matrix are useful when we have diagonal matrices, such as this one over here, with non-zeros for the diagonal elements only. So for example, if we take m to the power of 3, it's m multiplied by m multiplied by m. And if you multiply this out, you'd get 8s on the diagonal, or 2 cubed, and zeros elsewhere. So more generally, m to the power of some exponent is m multiplied by m e times. And m to the 0, being a special case, is the identity matrix. So recall that this identity matrix would have 1s on the diagonal and 0 everywhere else. Now if the matrix is invertible, then m to the power of minus e is the same as the inverse of m to the power of e. So that's representative of the inverse multiplied by itself e number of times. And because the definitions for matrices are parallel for real numbers, then the laws of non-negative exponents hold. So for example, if we have m to the power of e multiplied by m to the power of f, then we keep the base and sum the indices. And again, provided the inverse of a matrix exists, if we take the inverse of the inverse, then that gives back m. And if we take the inverse of m to the power of the exponent, then that's the same thing as m to the minus e, which is the inverse to the power of e. And taking the inverse of a scalar multiplied by the matrix is the same as multiplying the reciprocal of the scalar by the inverse of the matrix. And in a similar way to polynomials, we have the binomial expansion of m plus n, which is m to the power of 2 plus mn plus nm plus n squared. So this is not exactly identical to a polynomial expansion, because generally the matrix product is not commutative, but for matrices that commute, such as diagonal matrices, this term here would be 2mn.